Good morning, everyone. Hope everyone is having a good morning. Today, we're reviewing STEAM fundamentals. I'm Sunday Perez, Corporate Marketing Manager for CHC, and our awesome, amazing, awe-inspiring presenter today is Paul Campbell. He's our Corporate Technical Trainer and a great resource for all of you to keep in mind for future projects and questions. Our question and answer, we have a Q&A chat function at the bottom, two little chat bubbles, and then we also have our straight up chat function. I'm monitoring both. Feel free to ask any questions in either. I will catch up with you. Having said that, we have a full class, probably go as long as possible, and then we'll handle questions at the very end. With that, I'm going to hand that over to Paul so we can get started and get rolling.
Awesome. Thank you, Sunday. Good morning, everybody. Thanks for joining us today. We're going to cover, as Sunday said, some STEAM fundamentals. Most people who know STEAM either have a lot of gray hair, it's hard to tell on this closely shaved head, or you pick it up in the Navy or the military. STEAM's definitely a dying art, but it's still out there, and we just want to cover some basics and some fundamentals. So that's our goal this morning. With that, I'm going to go ahead and shut my video down until we get to Q&A, and we'll get rolling. We do have a lot of information to cover today. I'll try not to speed talk. I just want to make sure we're touching on some good fundamentals for you and make sure things are making sense. So let's get rolling. I'm not going to waste a lot of time on bullet points. Let's get into the heart of it. So one thing we need to know is if we light a matchstick, it'll heat a pound of water 1 degree, roughly 1 degree, okay? And it makes sense. It's called sensible heat, and the fact that we can measure it on a thermometer. Most of our hot water and chilled water systems, we are exchanging heat or generating heat in something we call sensible mode. So if we have 1 pound of water sitting at 100 degrees and we light 100 matchsticks, okay, or fire up a boiler, we're still going to have 1 pound of water, but we're going to increase its temperature. We're going to drive it from 100 to 200 degrees. All that makes sense. You can see it on a thermometer. The thermometer increases in temperature. We're doing something, okay? That's our life in a closed loop hydronic system. It makes sense. With steam, get ready, it doesn't always make sense. We're dealing with a phase change more than a temperature change. And that's where people have a hard time wrapping their head around it. If you think about going from ice to water or from solid to a liquid, you do that at 32 degrees. If you think about going from water to steam or liquid to vapor, you do that at 212 degrees. It's a phase change, but it's not a temperature change. And when we're dealing with steam, that's what's occurring, is this thing we call a phase change. It's hard to pick up on a thermometer. As a result, it doesn't make sense. It doesn't make sense. Okay, it's not sensible heat, it's what we call latent heat. And it's all derived in what we call a phase change. So if you can wrap your head around that, that's the first part of making sense out of a steam system. We are simply converting water into steam or into vapor, however you want to look at that, and it may or may not register on your thermometer. Okay, now if we put a pot of water on our stove and we continue to add heat to it, we're going to get some hot water at 212 degrees, but if we continue to add heat to it, we're going to turn all that water in our pot into steam. It's still at 212 degrees, but we've converted it all from liquid into vapor or water into steam, okay? And we do that by adding roughly 970 matchsticks to our 1 pound of water. So that's the amount of heat we're adding to convert water into steam. Another thing that's really important is when we convert water into steam, it grows, and it grows substantially. steam is much larger in volume than the equivalent water-based. So steam expands roughly 1,700 times in volume compared to trying to circulate water, which means we need much larger line size for low pressure steam applications. Couple, how do I want to say it, fundamentals again. Steam has its own motive force, meaning high pressure goes to low pressure. We don't need pumps to distribute steam through our system. We just need to get rid of the air and the cold condensate that are in front of it, and high pressure steam will naturally find its way out or circulate through our system. Okay, let's look at a steam property chart. And what we've been talking about up till now is basically atmospheric or 0 pound steam pressure. It boils at 212 degrees. Now, sensible heat, again, we don't really care about it, but let's talk about it. If we take 32 degree water and we light 180 matchsticks, it takes us from 32 degrees to 212. So that's where sensible comes into play. Latent heat is what we actually continue to add to that water to convert it all to steam. And total heat, well, that's simply latent plus sensible. And again, we usually don't care about that. The other one to keep in mind is specific volume. So low pressure steam requires a pretty good line size in order to transport it. Now, one thing I haven't touched on, if we run low pressure steam, in this case 0 pound steam, through a heat exchanger and we transfer the heat, we pick up 970 BTUs when we transfer or when we convert steam into condensate or steam back into water. This is what gets transferred into the other side of our heat exchanger. Okay, so that number we do care about. We care a lot about latent heat. We don't care so much about sensible or total, but latent heat is an important driving factor, especially on our heat transfer side. Now, just for fun, let's say our boiler can produce 100 pound steam. Let's look at those properties. Higher pressure should be better for us, okay? So if we're generating 100 pound steam, it boils at 338 degrees. We've got a sensible at 309 that we don't care about, and our latent is actually worse. It went from 970 down to 880. Okay, we actually get less heat, or less less heat transferred with high pressure steam than we do with low pressure steam. Now, a big advantage of high pressure steam is the fact that it requires a lot less volume in order to transport. Why is this critical? Well, if you've got a big facility and you're trying to get heat out to multiple buildings, you can do that very successfully by utilizing high pressure steam. You get a lot of BTUs through a small line size compared to trying to do that with low pressure steam. Okay, so in a nutshell, high pressure steam is great for transportation, getting it out through multiple buildings, multiple sites. Low pressure steam is way better for heat transfer. And hopefully that makes sense based on this steam property chart. Now, another thing to think about, if we take that 100 pound steam and we try to run it straight into a heat exchanger, and I know this slide isn't great, so forgive me, okay? Let's assume there's no pressure drop through our control valve. And we take 100 pound steam straight into our heat exchanger. We're gonna get 338 degree condensate that leaves our heat exchanger, heads into a trap, and then we dump it into an atmospheric flash tank. Well, part of that 338 degree condensate is naturally going to try to flash back into steam because it's got a lot of energy in it. So that is a loss straight out of our building. And in this flash tank, we're simply allowing the condensate to cool, and then it flows into a condensate receiver where we pump it back to the mechanical room. So one of the disadvantages of high pressure steam is the fact that we have some flash losses. Okay, have you ever been to Old Faithful? Good example of flash loss. All right, a lot of heat being lost to the atmosphere. Same thing in a steam system that's using high pressure steam. So in our case, if we're trying to use 100-pound steam for heat transfer, and we're dumping it into a vented flash tank, essentially we're going to lose 13% of our energy or our fuel bill straight out the stack or vent pipe. Okay. You'll notice as we drop our steam pressure, as we get lower in pressure, we reduce that flash loss, and it's easier to handle condensate that's at lower temperatures than it is at 338 degrees. If we look at what's happening inside a flash tank, keep in mind it tends to be a flooded vessel, and you have high temperature condensate that's flowing into the what we call a sparge tube, basically a tube with holes. So that hot water gets distributed evenly. Any flash steam that occurs above the water line can get vented out of the receiver. Now, granted, you can also capture this and use it for domestic preheat or something else in your process. But if you choose to vent it, it's going straight out through the roof. Actually, the colder condensate collects down at the bottom, and that simply gets routed to a receiver where, again, it gets pumped back to a mechanical room. Occasionally, you might be tied into, like Seattle has Central Steam, but they don't want their condensate back. And you have to be careful if you're dumping this down a sanitary drain, and the fact that most utilities don't want any temperature that's greater than 130 degrees going down their drain. So you might end up in a situation where you have a condensate cooler or a flash tank also tied into some type of heat exchanger where you can cool it or drop temperature before you send it down the drain. So this would be a good application for, again, a domestic preheat or something else in your system where you've got cold water available to drop the temperature of your condensate before you send it down the drain. A couple other fun facts. Commercially, we typically design steam systems for, I don't want to say it, steam distribution lines for velocities of 4,000 to 6,000 feet per minute. Industrially, you can run much higher than that. Obviously, there's a sound impact, but 4,000 to 6,000 feet per minute might not mean much to you. It doesn't to me until you start converting it. So 4,000 feet per minute, close to 46 miles per hour. 6,000 is roughly 70 miles an hour, meaning our steam is flying through our steam distribution lines. Okay, when you get on a steam job, it tends to be a little loud. This is one of the reasons. There's quite a bit of noise and velocity in a typical steam system compared to a water system that tends to run a little quieter, a little slower. The other thing to think about with steam, you might run into some factors that don't make a lot of sense to you. At least they don't to me. One of them might be steam boilers are typically sized based on boiler horsepower. This was asked earlier in one of our boiler classes. Hey, why do we have burners that are rated on horsepower? I'm like, well, that's how they do it on a typical steam job or large, I'd say a real boiler, a big boiler. But one of the things you might want to consider is some standard conversion factors. Okay, so one boiler horsepower is equivalent to about 33,000 BTUs an hour. So if you had a 100 horsepower boiler, that's about 3.3 million BTUs an hour. The other thing is, if you're really old school, you might get hit with something that's called square foot EDR. It's simply, it's how we sized boilers way back in the day when you'd go through a facility and just count up how much radiation there was or how many radiators were in a facility. And based on that square foot, you would back it into boiler horsepower, okay? So that's another way to size a boiler. How are we doing for time? Oh man, we are right on track. We got lucky. One of the things I do when I'm working on a steam job is I grab what I call a cheat sheet for conversion factors. Simply allows me to take some of those boiler horsepowers and convert them into BTUs that I'm comfortable with. On traps and condensate pumps, Also heat exchangers, you'll get condensate flow or steam flow that's in pounds an hour. For me, it's important to at least picture that in gallons per minute. So there's ways to convert it. But standard conversion factors, for me, it's just a friendly reminder of taking some of those steam properties and getting them back into units that I understand or work with on a more regular basis. I threw this in as kind of a general schematic, and we'll be referring to this throughout the hour here. But bear with me a second as I kind of talk this through. Let's say we've got a high pressure boiler in our mechanical room that's producing 100-pound steam. That 100-pound steam gets sent out through our system. We might have some, how do I say it, some applications where we require that high pressure steam, like a sterilizer, maybe an autoclave, something in our system that needs high pressure steam. If we're going to control that with some type of control valve setup, we come off of that, I'm going to call this a heat exchanger, but we come off of that heat exchanger with 338-degree condensate. It's too hot to touch or to transport, so we dump it into our flash tank. And again, that flash tank allows that steam to give up its energy, cool down a little bit, so we can route that condensate into what we call a condensate return unit, simply a receiver with some pumps. When this fills up, the pumps come on, one or two of them, and transfer that condensate back to what we call a boiler feed or a deaerator. This simply holds water for the boiler until the boiler requires more water as it's steaming, okay? We're gonna take that 100-pound steam and we're gonna continue it through our system. We might reduce it from 100 down to 15, and that 15-pound steam is really good for heat transfer. So we're going to run that, again, low pressure steam through a heat exchanger. In this case, the condensate's cool enough where I don't need a flash tank. I can take that condensate and dump it directly into a condensate return unit again, and take that low temperature condensate and pump it back to my mechanical room, where it sits in my boiler feed or my deaerator. Now, one thing about flash tanks, you typically tie those in for steam pressures that are greater than 15 pounds, simply because your condensate's warm enough where you need to give up some energy before you dump it into a receiver to pump or transport it back. If you were with us 2 weeks ago, we talked about general heat transfer. So I may not spend too much time on this, but one of the units we see a lot is some type of shell and tube heat exchanger. We've got a shell that we simply are transferring heat in. In this case, we've got a large inlet here and a small outlet here. Remember, steam expands 1,700 times in volume. It also shrinks 1,700 times in volume when it goes from steam to condensate or vapor to a liquid. And on the tube side, we're typically flowing water in, how do I say it, cold comes in down low, and hot leaves nearest the source, which in this case is the steam side. We always have to build in fouling for our heat exchangers because we don't know what kind of minerals and chemical treatment is going on within the system. So we basically oversize our heat exchanger to account for any fouling that might occur on the outside of the tubes as well as inside on the scale buildup. We add additional surface area to our heat exchanger to make sure it performs 5, 10, 15 years down the road. If you looked at a typical fouling factor chart, spec standards are 0005, which are essentially 20 to 30% additional fouling factor or surface area. If you get higher than that, you could be looking at 80 to 110% additional surface area, depending on the plant facility and maintenance, all the other variables that are flowing through that system. Essentially, shell and tube heat exchangers have quite a bit additional surface area built into them so that they can continue to perform as you get fouling and debris built up on the inside and outside of those tubes. Now, a typical installation, whether this is a fan coil, could be a unit heater with a coil in it. any type of heat transfer device. In this case, we're just looking at a shell and tube heat exchanger, but this could be any type of heat exchanger. And typically what's happening is we're constantly flowing through the tubes. It's kind of constant flow, okay? So the pump's constantly circulating fluid, and then we simply control the steam inlet based on leaving water temperature. So this valve modulates based on our set point out here required in the system. Now, if you want to screw this up, start lifting condensate. Now, one of the mistakes we've seen a lot of people make is they may assume that they've got, well, let's just call it 100-pound steam coming into this regulator. Okay, if this regulator is 100% open, 100 pounds of pressure is equivalent to about 230 feet of vertical lift, which means technically you could lift your condensate as it leaves the trap and leaves the heat exchanger. Go up and over a doorway, elevated return, whatever you're trying to accomplish. But what people forget is you only have that 100 pounds available when this valve's open. As we get close to our set point here on the water side, this valve starts to modulate closed. When it does that, all the steam that's in this shell starts to cool and condense, but there's no pressure to elevate or lift it to the elevated return. As a result, you kind of create an inverted P-trap, and this whole heat exchanger floods with condensate. Nothing's wrong yet until we drop below our set point, and now we open our control valve and we slam 100-pound steam or 338-degree water, or sorry, 338-degree steam into colder condensate. Some of that condensate flashes back into steam, and we get water hammer that's very explosive and will tend to tear up your tubes. So, recommendation on steam, always never try to lift it. Always try to go to a gravity return. Keep this bundle or your heat exchanger dry, and you will be just fine. But if you flood it with condensate and flash steam into it, you're going to have some problems. If you do have to elevate your condensate after the heat exchanger, you have no choice. We're going to recommend putting in a receiver here and physically pumping it versus relying on steam pressure to try to lift it. Hope that makes sense. If anybody's wondering how you might get air into a steam system, well, it tends to happen with vacuum breakers. So as steam cools and condenses, it also pulls a vacuum. So this is typically on a heat exchanger, and as you're pulling a vacuum, as that steam's cooling, it actually pulls this plunger down and allows air to flow into our shell of our heat exchanger, allows condensate to drain, but it also brings air into our system. It's not a bad thing. It's just something to keep in mind as far as you think it's a closed loop system, but you've got vacuum breakers allowing air in. If you're in a system that is steam-based, you do have options for generating domestic hot water, either instantaneous or semi-instantaneous with a little bit of volume. You do have options to generate some humidity or clean steam, if you will, for humidification purposes, where you're using RO or DI water. We can certainly help you with those applications. If you've got steam, it's certainly an easy option to generate domestic or clean steam. So back to our schematic. Let's talk about these couple of items here, which we call condensate return units and boiler feed units. What's critical about a boiler feed is that it needs to be controlled by the boiler. Okay, the pump does. So as the boiler is sending steam out to the system, its water level is also dropping. When it drops enough, it tells the pump, hey, I need some more water. So send me some of that stored water that you've got and come on in. Okay, so the boiler should be controlling its dedicated boiler feed system. The other thing that's really important with the boiler feed is we need a receiver that's sized for at least 10 minutes of storage. It takes a while for all that condensate to come back from the system on initial startup. So we've got pretty good receiver size sitting here on a boiler feed system. Okay, you might have a really large receiver. That's okay. It depends on the size of your boiler, but that's what it's doing. It's storing water until the boiler's ready for it. If you're in a bigger boiler system, typically anything over 15-pound steam, you'll typically be dealing with a deaerator. This is just like it says. We're taking air, or we're de-aerating the return water. So if you, Google's my friend here, but all we're doing is we're taking the condensate that's coming back from the system. We run it through some tray bars, kind of like a cooling tower with some media. We're trying to disrupt the return so that any air that's in our return water from a vacuum breaker or somewhere else in our system is getting vented out of this receiver or this pressure vessel. Okay. We also have some low pressure steam that comes in. It's more buoyant, so it's picking up air and it's heading it towards the air vent, so it gets out of our return. And then we also kind of have a warming bed here, so we keep this water that's being stored at temperature, so that when we send it to our boiler, we don't shock it or tear it up. So that's what's happening inside a deaerator. It's just like a boiler feed. It's just a little fancier in the fact that we're taking air out of the return water. Let's change our tune for a second and let's just focus on condensate return pumps. These couldn't be simpler. This is simply a very small receiver, typically sized for 1 minute of net storage, tied to a pump, and the pump is simply controlled by an internal float. So as this receiver fills up with water, the float raises and turns the pump on, and the pump starts sending water out of the receiver. It's that simple. You could have a simplex or a duplex. You can have a mechanical or electrical alternator, but essentially you're just running on internal water level as it's coming off a heat exchanger or any load in our system. A couple things to keep in mind. This is not a pressure vessel. Most condensate return units are not rated for pressure. A cast iron receiver is only good for 5 pounds of positive pressure. That's not a lot. So you have to watch your vent run. If it gets over 20 feet, most manufacturers are going to require you to have some type of overflow to get to drain. So if there's an electrical outage and this receiver starts to fill up and starts to raise water up in the vent pipe, you've got a way to get water out of the receiver so it doesn't overpressurize and doesn't go boom in our mechanical room. The other thing that's important, us as reps, we never know where this water's going. We don't know if it's going up and over a doorway into a boiler feed next door, or if it's going 500 feet into a mechanical room. So most condensate return units are sized for 30, 40, 50 pounds of discharge pressure. This can be a little problematic if there's no resistance on this pump. Okay, all condensate return units have a standard pump curve, and this is just looking at one of them, but you'll notice at 30 gallons a minute, this is 30 feet ahead. If we have resistance that's less than that, our pump's going to try to ride off the end of its curve every time it operates. One way to resolve this, if you're having pump issues on your condensate return units, add in our case, we add a circuit setter or a manual balance valve. We also put a pressure gauge on here, and we can create some resistance on the discharge of this pump to keep it operating on its curve. That's a really good way to extend the life of this pump that's in question. Okay? If you're going through pumps every 6 to 9 months, pretty good indication that you're riding off the end of its pump curve or performance curve. We try not to do that. How are we doing on time? Oh man, we are tracking. So guys, we've talked about condensate return. We've talked about boiler feed and deaerator. Let's talk a little bit about these little boxes here that we call traps. These are kind of a bit of a mystery in a steam system. What does a trap do? How does it operate? Let's talk about these guys. There's just there's a few versions to look at. We're going to look at this thermostatic. We're going to look at a what we call an F&T, and then an inverted bucket trap. and try to explain the differences. So what's a steam trap have to do? Well, it has to open in order to pass condensate and any air that's trying to get out of the system. Once we get steam, that trap has to close. Pretty simple. So let's talk about this thing we call a thermostatic trap. And these are much smaller in size, typically 1/2 to 1 inch. Kind of dedicated as far as maybe looking at radiators or small fan coil units. Nothing with a modulating load. They come in various configurations. But the key to this thermostatic is this element, this thermostatic element that's inside of it. It's filled with a water and alcohol mix. It boils at roughly 180 degrees. Okay, so on a cold system, you've got air and cold condensate that come in from the top and simply flow around this element back to drain. This is typically headed back to our mechanical room. Okay, I'm going to call it a drain, but that's our return. Now, once we get the hint of steam, to get rid of all the air and cold condensate in our system, steam's right behind it. Steam's going to hit this element and boil that alcohol water mix, and it now closes this off. So all the steam that is stuck in our radiator or fan coil or a little unit heater is stuck there. And we're going to get as much heat as we can out of that steam that's in that radiator. And it's not till it all cools down to less than 180 degrees that this element will open again and allow all that colder condensate to flow back to our mechanical room. Okay, so that's a typical thermostatic element. It traps steam once it's in your heat exchanger, and it's not till it cools down that it allows it to flow again. So that's what we're calling subcool. Doesn't work real well on a commercial version, but works really great on a residential type setup. Okay, now this is rocket science. We just looked at a thermostatic trap. What we call an F&T is a float and thermostatic. Okay. So this little element hanging off the side of the trap should look very familiar. That's our thermostatic element. Inside, we've also got a float. So we've got two things that are controlling kind of condensate flow and airflow. If you think about this, if we've got air that's coming back from our system through this top connection, there's no easy way to get around this float and this seat to return, to get back into our return or back into our mechanical room. That's why we have a thermostatic element. So on initial startup, if we get air that's coming back from our system, it flows through the thermostatic element and is free to flow back into our mechanical room. Now, once we get the hint of steam or warm condensate, this thermostatic element goes closed, right? Anything greater than 180, this guy is out of the picture or goes closed on us. Now we're relying on the float to handle increase in condensate and allow condensate to exit the trap and get back to the mechanical room. So you really have two control devices, one thermostatic and the other being a float. Pretty simple. Typical for an F&T, at least smaller sizes, there's 2 inlets at the top and also 2 outlets at the bottom. You get to choose how you want to pipe it. Here's how we would recommend it be installed. They never get installed this way. This up at the top would be our heat exchanger or a fan coil, whatever we're serving with steam. We've got a Y strainer here to protect the internals of our trap. We've also got a test valve so we can come over and see if we're getting air and condensate out of this trap versus live steam. And then we're sending it to a gravity drain. Ideally, we're looking for 15 to 18 inches below our equipment. So when that main steam control valve goes closed, we still have ½ pound of pressure to adequate pressure to force our condensate through the trap and ultimately into gravity drain. Be careful if you're selecting traps. A lot of guys will tend to select them for incoming steam pressure. That only works if your control valve is 100% open. We'll tend to select them for that height difference between the bottom of the heat exchanger and the trap location. Typically that's a ½ pound. On higher steam pressures, you might select that for 2 pounds of pressure, but you'll notice that it definitely has an impact on your capacity, or how many pounds an hour you can pass with that trap, based on the opening of that steam control valve. If you think you have a trap that's failed, a lot of guys will try to use temperature crayons as one way to troubleshoot it. But the guys who troubleshoot a lot of traps tend to use a listening device, or I want to say that's ultrasonic, but that's not right. They will use a listening device to physically monitor the trap. You can hear condensate or water gurgling through it. You can also hear steam screaming through it. So a lot of the traps that you might think are good based on a crayon turn out to be bad once you physically listen to the condition of them. These aren't cheap. They tend to run $4,000 to $5,000 for a listening device, but guys who are heavy into trap surveys, they swear by these. Remember, there's not a big temperature change in the steam system from steam to condensate, so a crayon is a tough way to monitor a trap. So typical F&T, a normal failure tends to be closed, and they work really well with modulating loads. So we see these a lot on commercial heat exchangers, anything in a steam system really. Let's talk about the last style trap, which we call an inverted bucket. Looks a little different than an F&T, and the fact that you could think about this as kind of an inverted tuna can or coffee can. So you've got a lid on this, but the bottom here is completely open. You tend to have a small hole in the top of the lid that allows air to escape and get back into our mechanical room. Okay, so on initial startup, cold condensate and air can either flow around the bucket or go through the bucket and get out of the mechanical room, or sorry, get back to the mechanical room. If you get a steam bubble that comes into this trap, it's going to physically lift the bucket up, okay, and seal the trap. It's not till the steam gives up its energy, cools and condenses, that the bucket drops. So typically with an inverted bucket, you can hear you can't hear the bucket raise, but you can definitely hear it drop, and it tends to cycle. Now a little fun fact for you: if you're using inverted buckets, you need to prime these prior to startup, meaning you need to fill them full of water. Okay, that's what this little port is up here. If you don't do that, if you've got a dry trap, you have potential for steam just to get around and bypass the bucket altogether. All right, at least until it fills with condensate. So you might have a few bad cycles before that happens. Inverted buckets, one of the challenges, normal failure is open. So if it does fail, the bucket tends to just sit at the bottom of the trap versus modulate up or down. That can cause some problems. A couple other traps, I won't spend a lot of time here. Thermodisc is one. This tends to be really loud. It's not something you want to put above somebody's office. It is all stainless, so you could put it outdoors. It works more on a steam hammer application. The fact that it traps a little water up at the top, or condensate. When steam hits it, it physically flashes and causes the disc to close. It's not until that steam cools and condenses that the disc opens again. So these have limited applications. We've also seen some Venturi and orifice style traps. There's really no maintenance here. The only downside would be that you're constantly bypassing some steam or condensate depending on your load. But I don't know much about these, so I kind of have to leave it at that. Other than, I think facility guys love them because there's nothing to service. But if you don't size them right, you could have elevated condensate temperatures back at your mechanical room. We're running a little early, look at that. So a couple other things. You'll notice if you've got long horizontal runs in your steam distribution lines that you might have what we call a drip leg. anytime before some type of reducing valve or control valve, you tend to have these things we also call drip legs, okay? And if you think about steam flowing through our system, if it's moving at 50 miles an hour through our system, and all the heat exchangers over to the right here are satisfied, this valve would be closed. So you've got 50-mile-an-hour steam that's hitting a stop sign. And part of that steam is going to cool and condense, give up its energy, turn back into condensate. So in order to protect this valve, you have to be able to get the water or condensate out of that system. So that's what we're doing with the drip leg. We're allowing any moisture to get out of the system. So typically if you're running 100 to 300 foot horizontal runs, you're going to have 1 or 2 drip legs installed. This is what a drip leg looks like, okay? It's simply a way for condensate to get out of our system. And remember, if you've got steam moving at 50 miles an hour, there might be some droplets or condensate that's sitting in those lines that's going to get pushed or carried along. You want to get them out of the system before they hit a valve and do some major damage. So ASHRAE's got configurations for you based on startup criteria. We can help you with some piping schematics if needed, but all you're looking at is I don't want to say it, a larger diameter to collect condensate and get it out through a trap. Now, one last thing, and I won't bore you with this, but if you're looking at some type of reducing station, if you're taking 100-pound steam down to 15, we tend to use just a pressure reducing station. The main valve doesn't really know what to do until you tell it to respond for pressure or temperature, but you'll notice that there's a seat right here, okay, a metal seat. One thing that's critical when you select these valves is to make sure that anytime it strokes, that it's stroking to 50 or 100% capacity. You don't want to operate near this seat location simply because we get a lot of velocity that rolls through here, and we can actually, it's like taking a drill through it, but you end up with something we call wire draw. And at that point, you've got a valve that's trying to close, but you still have steam escaping and getting out into your system. So we try to avoid that situation. Okay, but if you're looking at a main valve, typically you've got some type of, I want to say a pressure control downstream. We call it a spring pressure pilot. You could also do it based on temperature or both. And this might be a typical setup for you. If you're trying to do a 2-stage reduction, you might have 100-pound steam coming back from our system. We might reduce it down to 70 or 65-pound steam here for sterilizers or autoclaves, and then you might take that 65 and reduce it down to 15 here for better heat transfer as it heads to a shell and tube style heat exchanger or domestic water application, whatever we're doing on our steam side. Keep in mind, reducing stations take up a lot of space. You might be hard pressed to get this on a 15 to 20 foot wall simply because you'll notice that each one of these pilots needs 10 pipe diameters downstream to accurately monitor steam pressure. So all that takes up quite a bit of space. Okay, max pressure drop through a reducing station is typically 100 pounds. You can do 150, up to 150, but you're asking a lot of that valve in particular. So typically we see a 2-stage reduction occurring. And you never want a line size, okay? We always size based on the load or pounds an hour that's going across that valve, as well as the pressure drop. Okay. Now, Sunday, I'm going to ask you real quick. So we're sitting at 10:45. I'm wondering if there's any questions we need to deal with.
Yeah, we've got.
Or if we should.
We have 1, 2, 3, 4, 5, 6 questions.
Okay, well, maybe this is a good time to deal with questions. And if people want to stick around later, we can talk quickly about a boiler explosion that occurred in Tennessee. We didn't have anything to do with this, but if you want to see some of the damage that can occur when the steam goes bad, we'll run you through this real quick. So Sunday, yeah, let's start with questions if we could, if that's okay with everybody.
Okay, so first question. What if you had a check valve on your condensate line? Could that help you be able to lift but not flood the tubes?
Oh, yeah, good question. So let me bounce, hang on, let me bounce back. I don't know that there's any real, yeah, let me go to this one right here. I don't know that there's any real good way to lift condensate other than installing a pump to elevate it. If you have a check valve right here, the thought is, okay, this won't be allowed to backfeed through the trap and flood the heat exchanger. The downside is, so I understand the point or a question. The downside is with this valve closed and this vacuum breaker port open, there's really no pressure to open the check valve. So any steam in the shell is also going to cool and condense and create and not be able to move, if you will. Okay, so it's going to get locked in the shell until the steam valve opens again. So a check is a good approach, but it's still a problem application. And guys, I tell you in general, if you want to tear up a heat exchanger, start lifting condensate. Every job I've seen where they lift condensate, they're always complaining that their heat exchanger only lasts 6 months to a year, and regardless of the size. Okay, but yeah, good point on the check valve. I still think it's a problem.
Is clean steam the only steam that is recommended for humidity in air systems?
Oh, yeah, another good question. So with clean steam, it depends how you're getting, how you're humidifying your air. With clean steam, all we're doing is we're protecting, we're taking dirty plant steam. Let's see if I can go back here. Yeah, forgive me. We're taking dirty plant steam that's chemical laden, and we're simply running it through a coil. Okay, there's simply a U-bend coil that's in here, and we're surrounding it with RO or DI water to generate pressurized clean steam that you could use for humidification or blow directly into your air handler coil for distribution or humidification. There's also point of use, so you could get individual units that generate very low pressure steam or 0 pound steam that you could use for humidification. An advantage of a clean steam generator, you can get 15, 20 pounds of clean steam that you could distribute. So it's kind of one, how do I want to say it, one point of maintenance versus multiples. It really depends on your facility and what you're trying to accomplish. But ultimately, you don't want boiler chemicals getting sprayed into your air handler for distribution on humidification. That's kind of a no-no.
Okay. Do the condensate pumps have negative suction?
I'm going to say no. We do run into vacuum systems where we're generating a vacuum with the condensate return unit. Those run a little differently, and the fact that they are trying to pull a vacuum and get the air out of the system quicker by forcing a vacuum through the traps and kind of speeding the steam, how do I say it, the steam distribution through the system. But in general, a condensate return unit is always dealing with a flooded suction. So once this receiver fills up, the pump's flooded with water, so it's not running in a negative situation. I hope that answers the question.
Okay. What slope for steam and condensate piping?
Sunday, can you repeat that?
What slope for steam and condensate piping? There's no further.
Yeah, and forgive me, that the question's not making sense. So yeah, if you'd like to clarify that or shoot an email, we can certainly take that offline. That's no problem.
Andy, if you want to clarify that, that'd be great. I know you have another question in queue. Okay. When are steam systems typically used?
When are they used?
Mhm.
A lot of school districts. You'll see them a little bit remote where they're going to run on number 2 diesel, light oil, sometimes propane or natural gas. You'll see them in hospitals quite often. And if you're industrial, steam is kind of the basis out on the industrial side. On the commercial world, definitely a dying art. A lot of guys don't understand steam, and they're the guys who do are taking that knowledge with them when they retire or punch out of the industry. So new engineers don't understand it as well. Efficiency, it's not 100% efficient compared to condensing boiler style. It's also a very forgivable system. But you can typically tell a steam job when you roll up on it. Most of the windows are wide open. All the classrooms are very warm and hot. The comfort control can be questionable. Honestly, trap maintenance is one of the real, how do I say it, one of the real sticklers or problem sources for most people on a steam job. It depends on your campus and what you're trying to accomplish. But yeah, how do I say it? The uses vary. But yeah, good question.
Can you have high pressure condensate return?
Certainly, yeah. And I assume you're talking about the discharge of the pump versus the inlet to a receiver. On the discharge, yeah, we can do whatever you'd like as far as high pressure goes. On the inlet, you have to be very careful. Receivers, are only designed for 5 pounds of positive pressure. If we have to work outside of that, maybe we get into a pressure vessel that can accommodate that, an ASME vessel. And yeah, we just have to make sure we size our pump properly. But yeah, other than that, no limitations.
Okay. Questions keep coming in, Paul, so.
Okay, that's fine. Well, yeah, we'll pass on the boiler explosion then, or I guess we can poll people there.
Yeah. If we treat with food grade chemicals for, it says STREM treatment. I'm not sure if that's the proper word or if it's a typo. Does that resolve the issue for humidification?
Oh, I would say yes. If you look at Seattle specifically, they deliver food grade steam to, or they distribute that. So you don't need double wall heat exchangers particularly. And yes, you'd probably be okay on humidification under those requirements. Obviously, that's going to be subject to your local inspector. But in general, I would tell you, yeah, that does open some doors for you. Yeah, very good clarification for sure.
Great. What are the advantages of using a steam system versus any other system?
Yeah, that's loaded. You don't need a lot of pumps other than your typical condensate return units or boiler feed if needed. It can be a bit of a simpler system in the fact that I don't want to say it takes care of itself, but your main concern would obviously be the boiler. And depending on the layout of your system, you may or may not need multiple condensate return units. If you can get it all back to a boiler feed without having to pump it, it becomes a pretty simple system. So in that aspect, that's an advantage. Disadvantage, I would think, would be efficiency might affect you. You might need to add an economizer to the boiler venting to up its efficiency. An advantage on the boiler, you could run it on biodiesel, propane. You could run it on light fuel oil, different fuel sources than you might be able to accommodate on today's standard condensing boilers. Forgive me, yeah, it's a really good question. It's loaded in a response. So yeah, how do I say it? Design criteria might be another one. If you can find an engineer who's comfortable with steam, that's great. There's a lot of individuals who might struggle on that front.
Okay. We have clarification on the slope question.
Sure.
Do steam and condensate pipes require slope? If so, what slope should they be?
That's a good question. So condensate lines, I want to tell you it's 1/4 inch per. See, this is where I'm gonna fall down. 1/4 inch per foot. Yeah, it needs to be graded. I can refer. I want to say it. I can follow that up with a better response as far as the grading goes. But yeah, it does need to slope, or I don't want to say it. You do need to pitch it, so it naturally falls.
Yeah.
But I want to tell you it's a 1/4 per foot, 1/4 inch per foot, but I could be off on that.
Yeah, we have, thanks, Brian, for your input. One of our attendees responded to the slope question. So to drain water in the condensate, the pipe has to be sloped. Common would be the same drain slope as waste drain, 1/4 inch per foot or 1/8 per foot. What's recommended? Steam slope of pipe, should it be sloped back to the boiler or sloped to the load? So.
Yeah, really good point. If you think about old boilers in homes, a lot of those were just gravity systems, and they worked on vapor pressure, well less than a pound of pressure, and the steam would simply rise up. It would head over into a radiator. It would get trapped. The condensate would naturally return back to the boiler. There were no pumps. It was some math, but it was. I'm going to say it. You might end up with a coal or wood-fired boiler that was generating steam, and also generated the Hartford Loop, which we didn't discuss today. But that there were a lot of homes that blew up because the boilers weren't piped right. So yeah, a little bit of steam history.
Okay, do condensate extraction pumps have negative suction?
We're going to have to clarify extraction pumps. So I don't know if you're pulling from a pit. I'm not sure of your application. Typically, we love to see a receiver versus a pit style, simply because you're dealing with warm water, and NPSH or cavitation can be a big concern if we're trying to lift that water. So we have to be very careful that we maintain a flooded suction versus pulling some type of vacuum or negative pressure. So yeah, again, if I can help clarify your specific scenario, glad to do it. There are some cautions when you're dealing with higher temperature water, because it is an open system, or you have a receiver that's vented to atmosphere. So you have to watch NPSH. Really good point.
I'm going to skip one because it has to do with explosions, and I think that leads into your video.
Yeah, it's just a few slides. I just don't know if we have time for that.
Okay. Well, we still have quite a few attendees hanging on. I think everyone wants to see what's going on. So I'm going to move on to the next one, and then we'll go back, or we can do that now, whichever.
Let's do that now, Sunday, if that's okay.
So one of the questions is, what causes steam systems to explode?
Yeah, let's talk about it. So guys, real quick, and forgive me if I'm running long on you. That's not our intent. It was just a lot of information to cover today. Let's talk about what can go wrong in a steam system, because there's been some questions there, and here's what can go wrong in a steam system. Okay, this is a manufacturing plant in Tennessee. This isn't where the boiler's designed to operate, but this is its final resting spot. What you're seeing on the front of the boiler is the roll-up door for the mechanical room. Nobody was killed in this. The facility guy his hearing's not great, but he survived. You can see the scaffolding that was near the boiler. You can see the gas train that's sitting on the wall. This is what happens when you dry fire a boiler. The burner kept, how do I want to say it, continued to fire or was in operation, and yet the boiler ran out of water. So the operators heard the boiler ramping out of control and decided he should go over and manually input some water. When he did that, you've got a superheated vessel and a little bit of water that hits it, and next thing you know, it's flying across the the fabrication floor. This is where boiler started its life. You can see the flue connection right here. You can see an inspector going, wow, that went for a ride. They've got some softeners on sale, so you might see these on Craigslist. You can see where the roll-up door was, okay? And now it's sitting on top of or in front of the boiler. If you look at the rear or the mechanical room, you can see what would appear to be a boiler feed or a deaerator sitting over here on the right. You'll also see what's left of, well, there's also a second boiler in the mechanical room, and then here's the boiler venting. Okay, this is the rear of the mechanical room. Obviously, it went boom, and it went big. You can see the rear door for that boiler that flew about 300 feet from the mechanical room. These typically weigh 800 to 1,500 pounds. They're full of refractory or concrete to protect the steel. Took out a car and a walkway on the way to its final resting spot. And again, luckily nobody was injured in this, but definitely did some damage. Let's talk about why it failed, why there was problems. Here's the linkage off the boiler feed or the aerator. It's disconnected. Okay, they were manually feeding the boilers with water or makeup water. A facility guy was doing this. This is the contact for the low water cutoff. It's fused or welded together. It obviously wasn't being checked for blowdown or proper operation. If you look at this float, when there's no water in the bowl, this float should be physically down, not stuck in the up position. If you're the boiler, you think you've got water in this because this float is telling you you do. Obviously, this was never checked for blowdown or safety concerns. Here's what a typical water level, or how do I say it? McDonnell Miller 150, which handles the makeup water as well as the burner control. It works on kind of a sight glass sitting off to the side and monitors the water level sitting inside the boiler. Okay, this float raises up or down based on the amount of water that's in the boiler. On a real boiler, you're supposed to blow this down on a daily basis and make sure that first your boiler feed pumps start, and second, that the burner shuts off if it runs out of water, okay, or the water level gets too low. Obviously, in this case, the pressure was on production, not on safety. There was also some jumpers on the burner side, burner control side. This is just a good example of what can happen when shortcuts are made. And the pressure was on production, not on safety. If you're manually feeding some high pressure steam boilers, all bets are off. Because if you're not paying attention or you get busy with lunch or Angry Birds, bad things can happen. Okay, so that's what can go wrong in a steam system. Now, obviously boilers have safeties and controls built into them. We try to avoid booms. Anything typically over 15 pounds requires a dedicated operator on site to prevent some of these problems. That might be another downside to a steam system is you need some, I don't want to say it, you need good personnel to run it and maintain it. Okay, Sunday, I think that's it for us.
We have 2 more questions, and the people are
okay.
We have quite a few people still hanging.
Yeah, I'm still here. Thank you, guys.
Are tradesmen being trained in STEAM these days?
I would say no. That's a really good question. One of our most popular classes is STEAM Fundamentals, simply because nobody's getting any training on it. The only training I'm aware of is military or Navy, and most of those guys are used to 1,000 to 1,600 pound steam pressures. Yeah, they're not teaching it in school that I'm aware of. And again, most engineers that I'm aware of don't have a lot of comfort level on steam, simply because it's you kind of learn by the school of hard knocks in a lot of ways. As far as reference material, Dan Holohan puts out some great really good reads on steam. So if you're looking for that, I would look up Dan Holohan. He does some great personal group training, as well as some of his reads or literature are fantastic.
Okay. And our last question. In your opinion, what steam pressure do you feel is best for domestic water heating? High pressure or low pressure?
Low pressure all day long. 15 pound or less is perfect for domestic water production. I don't want to say this. If you're trying to maintain 140 degrees in a domestic storage tank or generate that, and you've got 212 to 230 degree available in low pressure steam, perfect. Lots of potential there. If you're trying to develop 140 degree domestic water with 340 degree 100-pound steam, really tough to control. So you end up with a lot of, I don't want to say it, water fluctuations with high pressure steam. So yeah, 5 pounds or less, honestly, would be great for domestic water, because your load varies considerably. Also, having a storage tank is a really good thing in a steam domestic hot water application, simply because the loads vary so dramatically. Yeah.
We just
ask me how I know. That's a really good question.
We just had one comment that said operating engineer apprentices are taking steam and boiler classes through PCC. So.
Oh, there you go. Okay, thank you for that. Yeah, I wasn't aware of that. Okay. Listen, I apologize for running long today. That's never the intent. Appreciate all the good questions.
Great. Thanks, everyone. We appreciate you all hanging on and getting to view that catastrophe with us that Paul shared. Hope you all have a great rest of your day, and we look forward to seeing you in the next class.
All right. Thank you, Sunday. Thanks, everybody.
Thanks.